What's up, everybody? Welcome back to another day of proof set theory and logic. Today, we're going to construct the rational numbers. It's going to be fun. So if you recall, really quickly, let's do a recall. Though I will need to grab a different marker. This one is not as good as I thought it was. Let's see. Okay. Quick little recall. So let A be a set, and let sim, this tilde, be a relation on A. We say that relation is an equivalence relation if it is reflexive, i.e. A is similar to A for all A's in big A, symmetric, i.e. A is similar to B implies that B is similar to A for, I'll write it this way, for all AB in A, and transitive, i.e. A is similar to B and B is similar to C implies that A is similar to C. Let's make that tilde a little bit better. For all A, B, and C in big A. Okay, so equivalence relations, just relations that are symmetric, reflexive, and transitive, yeah? What are relations? Does everyone remember what a relation is? Just a subset of a Cartesian product of sets, right? And so a relation on a set is a subset of the Cartesian product of the set with itself. So just ordered pairs of stuff. Okay, when that subset of ordered pairs has these three nice properties, we call it an equivalence relation. And equivalence relations are cool because we can do some nice stuff with them. So define the equivalence class of an element little a and big A to be the set, we'll write bracket A, consisting of all B in big A, such that A is similar to B. Okay. A fact, if tilde is an equivalence relation on big A, then, and we proved this last time, if the equivalence class of A is not equal to the equivalence class of B, the intersection of those equivalence classes is empty. Said another way, the intersection of the equivalence classes is not empty implies that the equivalence classes are, in fact, equal. Okay, so equivalence relations, very nice. The picture you want to have in your head here is the following one. Here's A. Here is what an equivalence class does. It slices it up into lots of different pieces. For each piece, you can pick any element in there, some A, then this whole piece right here is the equivalence class of that element. If this is B, then this whole piece here is the equivalence class of B. And you can pick whatever thing you want in there to generate the equivalence class. All right, totally fine. And once you do, effectively what the equivalence relation has done is partition the set. It's cut it up into pieces. It's like a big old pizza, and the equivalence relation slices it up somehow. Yeah? Cool. And then instead of having to talk about, little chunks of your pizza or a specific spot on your pizza, you can talk about a whole slice. Kind of nice. All right. So that's the whole deal of equivalence relations. We looked at some last time. We looked at, for instance, you could talk about integers mod 5. That is, you could look at integers and say, hey, take an integer. How much more is it than a multiple of 5? Is it a multiple of 5? Then it would be 0 more than a multiple of 5. Is it 1 more than a multiple of 5? Then it would be in the equivalence class of 1, right? And so on. So we looked at that last time. Now, today what we're going to do is we're going to construct the rational numbers. So kind of fun. There's a lot of different ways to do this. We're going to do one particular way that's not too bad. So we're in section 4.3, the rational numbers. And to be clear, we will not say all you can say about the rational numbers, which is quite a bit. Yes? What do we got?
Yes. I have a question about equivalence classes. In that slice, is everything equal to that?
Okay, so the question is for an equivalence relation, is in each slice everything equal? It depends what we mean by equal. Their equivalence classes are equal, right? So if you have like A1 and you have A2 somewhere else in there, then this whole set here is still the equivalence class of A1, which is the same as the equivalence class of A2. But A1 and A2 can indeed be totally distinct. Does that make sense? We'll see a good example here. Here, I'll give you an example right now. So think about fractions. And this will maybe lead into how we'll talk about the rational numbers. Just in terms of symbols, is this the same collection of symbols as, say, this? No. They are different in terms of, like, writing numerals with lines in between them, right? But in terms of what we intrinsically understand them to represent, they are the same number, right? That is, the equivalence class of this thing and is the same as the equivalence class of this thing. Like the ratios of integers for which the ratio is like 0.5, right? That is the same. Okay.
So everything in there is the reflexive, symmetric, and transitive.
Okay, so everything in there is reflexive, symmetric, and transitive is what you're asking?
Yeah.
Well, none of the things in the set are reflexive, symmetric, or transitive. Since, after all, the thing that's reflexive, symmetric, or transitive is the relation itself.
It's a relation between everything in equivalence class A.
No, not the relation between everything in the equivalence class A. Just the relation in general on the whole set is reflexive, symmetric, and transitive if it's an equivalence relation. Certainly, the equivalence classes inherit that relation, restricted to that, equivalence class. But yeah, so effectively, I think what you're saying is, so if here, I'll just doodle it here. So if you look at, say you have two different elements, A and B, that are not equal to each other, but A and B have the same equivalence class. What does this mean? Well, what this means, this says that the set of, I'll write x's, such that, let me make sure I keep it in the same order, B is related to x, and let me quantify where these are. X is in A, such that B is related to x, and the set of, I'll even use a different letter, even though we could just use x yet again. I'll say y in A, such that A is similar to y, that these are the same sets. That's what having the equivalence classes be the same means. And it's totally possible to have things be different, yet have the same equivalence class. Let's do the example we did last time with, let's look at the one we said for integers. We'll write this to mean that, what did we do? We said, we use exactly the same wording, same remainder after division by 5, right? So this would be if b minus a equals 5n for some integer n. So if we wrote it like this, b minus a is equal to some multiple of 5, and use that as our equivalence relation. You can verify that it is indeed an equivalence relation. Now, let's consider two different numbers. So what about, say, what? 1 and 6? A great choice, yeah. So the equivalence class of 1 would just be the set of all, I'll write it as A's in Z, such that, let me keep it in the right order, what? 1 is equivalent to A, which, if you notice, is just the set of A's in Z, in the integers, such that, just writing this right here, A minus 1 equals 5n for some n in the integers. What's another way of writing this? This is just the collection of A's in the integers, such that A is equal to 5n plus 1 for some n in Z. Another way of seeing this is 5n plus 1, where n ranges over all the integers. So this is the set, all right, this way of 1. Let's subtract 5. What would we get? Let's add 5, 6. So that's n is 1 and minus 1. And then we can take off 10. Or we can add 10 and get 11. See what I'm saying? Wait, did I do that right? Yeah? Yeah, minus 10 plus 1. Okay, 9. Yeah, good. Okay, and so on and so on. Yeah, perfect. Okay, what's something that has the same equivalence class? Easy to tell. Just pick any one of these guys. Yeah? Let's see it. So if we pick, for instance, let's do, oh, here, I'll kind of, this is not great board work, but whatever. Let's do the equivalence class of, say, 6. Well, this is the set of A's in the integers, such that, skipping this first step right here, I'll write A. So it'll be A minus 1 is 5n, but just if you permit me to go A is 5n plus 6 now, for some n in the integers, now you can just directly go through and compute this. What if you take n is equal to 0? Then you just get 6. What if you take n is equal to 1? Well, then you get 5 plus 6, that's 11. N is equal to minus 1? Minus 5 plus 6, you get 1. And see how it keeps going like this? So you get minus 10 plus 6, you get minus 4. What? Let's do 10 plus 6, you get 16, right? And so on. Look, it's the same as that one. You're just, you know, since there is no actual like middle of this set, I'm just trying to write out what this big old set, you know, has in it in a kind of obvious way. It's the same thing. We're just kind of putting this one in the middle when we write it, right? Does that make sense? So quite clearly, 1 and 6 are not the same integer. However, they have the same equivalence class. Does that answer your question, kind of? Or does that make some sense? Everyone feeling this? Is it hitting home all right? A little bit? Okay. Basically, the whole idea of it is, hey, you got some stuff, a big old set of stuff, and you have some way of describing when two things are somehow equivalent. And by equivalent, we mean when two things belong to a relation where that relation has these nice properties of symmetry, reflexivity, and transitivity. That is, all of the regular good old properties enjoyed by the equal sign. And we can take all of the things that are equivalent under whatever relation we have, and we can just put them together in a big old group and talk about that whole group of things at once. That's why it's nice. You can think of it almost like a, I don't want to throw too much additional terminology or anything here, but it's like a quotient, like it divides things out, right? It divides out like the difference between the things that belong to the same equivalence class. That is, if you have a set A and an equivalence relation on it, you can make a new set where you can kind of mod out, divide out by the equivalence relation, and just make it equal to the set of equivalence classes for all the elements. And so if two things have the same equivalence class, then they use two different things if they have the same equivalence class. It only shows up once here since the equivalence class is the same, and sets don't have repeats, right? Oh, okay. So it's like a way to take, for instance, all of the integers and turn it. So if we have, like, for instance, like we take z and we quotient out by equivalent mod 5, this would just be the set of equivalence classes 0, 1, 2, 3, and 4. Does that make sense? It's like, hey, you've got all these numbers, but if we only care about what their remainder is after division by 5, there's only 1, 2, 3, 4, 5 possibilities. It can be divisible by 5. They could be 1 more than a multiple of 5, 2 more than a multiple of 5, 3 more than a multiple of 5, 4 more than a multiple of 5. But once you're 5 more than a multiple of 5, you are, again, a multiple of 5, right? So it's a way to take something huge and slice it up. Does that make sense? Sweet. All right. This is why we care about equivalence relations, because they let us take some sort of a large and unwieldy set and make it into a much nicer and smaller set. That is, if you think about what we did so far, we did a lot of operations that involve making sets bigger, right? We took a set with another set, and we took their product, right? Now this is like a bigger thing, in a sense. Yeah? Like it's got more stuff in it in general, as long as one of the sets is not the empty set, right? Okay, so you can put sets together, make bigger sets. You can take a set, you can do a power set, make a much bigger set, the set of all subsets, yeah? Okay, now what we're doing is we're talking about how to take a set and make it smaller using another set. Does that make sense? That is, we're using the relation, assuming it's an equivalence relation, and we can take a big set and do this operation of sending things to equivalence classes to kind of cut it down. Okay, group things up. Kind of nice. So let's do that with the rational numbers. So here's the idea. Okay, here's what we're going to do. Okay, so just in terms of symbols, the fractions 1 over 2 and 2 over 4 are not the same. Yeah, just in terms of symbols. Like those are different. I've written different things on the board, right? You can tell them apart. Okay. But we understand them as being the same. That is, nobody would be upset by the statement 1/2 equals 2/4. Yeah? Since 1 times 4 is equal to 2 times 2. You agree with that? That is, if I multiply this side by 2, both sides by 2, and both sides, right, by 4, I can get rid of all the denominators and just turn it into a nice statement about integers. Yeah? Okay. So what's going on? That is, when we talk about the rational numbers, it's easy to think of it as we're talking about fractions, but we're really not talking about fractions, right? After all, 1/2 and 2/4 are different fractions. They are different, collections of symbols. But we treat them as the same number in the rational numbers, right? Can anyone see what the construction is? That is, they belong to the same equivalence class, right? We're going to create equivalence classes of fractions, like formally, these fractions, and we'll use these when we do operations with the rationals. That is, it doesn't matter which thing you draw from your equivalence class. You can use any one of them to represent the exact same number because we're talking about equivalence classes, not about specific fractions. Okay, so here's the setup. Here's how we actually go through and construct the rationals. Here's the idea. So here's the setup. Let us write f to be the, well, make sure you're in the same order. Okay, yeah, z cross the naturals. Z cross n, the naturals. Recalling that here we do not take 0 to be a natural number. Okay, so we take the integers cross the naturals. We'll take this, all right? Then here's what we're going to do. Define a relation on f, let's call it tilde, via AB tilde CD, if and only if. Well, let's think of these like fractions, where the first thing is the numerator, second thing is the denominator, since after all, we don't want zeros in the denominator, yeah? Okay, what could we do? How could we do this? That is, when is A over B equal to C over D? Well, would you agree that it must be AD equals BC? Yeah? It's a good way to use only the, multiplicative structure of the integers and naturals. Okay, so let's use that. Okay, so if we use that as our setup, then what we will do is we will construct the rational numbers as this thing's equivalence classes under this relation. Yeah? Making some sense? It feels like it's like needlessly complicated, but what I guess I'm trying to point out is that it's not needlessly complicated. What it captures is what you already intrinsically are doing every time you deal with the rationals, like without even trying. When you replace 2/4 by 1/2, you are just automatically going like, okay, it doesn't matter which thing I pick to represent this equivalence class, it's the same, And that's, it feels like when you put it into words, right, like actually formally write out like what's going on, it feels complicated, but I hope to convince you that none of this actually is complicated. It's something you automatically do in your head and have been doing in your head automatically since you were a little kid in grade school. Equivalence classes are extremely natural. So let's prove a fact. The relation tilde defined on f above is an equivalence relation. Okay, so how would we show this? What would we do? How would we prove this? Well, we must show this relation is reflexive, symmetric, and transitive. First, we show reflexivity. Let AB belong to F, which, recall, is the integers cross the naturals. Okay, then okay, here, let me write like this. So when is AB similar to CD? That would be when A times D, so first things 1 times the second things 1, these two get paired up, and these two get paired up. Yeah? So if we wanted to show AB, terrible writing. If we want to show that AB is related to AB, what would that mean? So if I'm filling in the blanks right here, then blank, so AB is similar to AB. We'll match up first with last, and these two. AB is equal to BA, would you agree with that? Okay, so AB is indeed similar to AB. That's the requirement. This just comes from the commutativity of multiplication on the integers, yeah? All right, so not too bad. That is, this relation is reflexive. Okay, now if we continue this proof, let's do symmetry. Okay, suppose AB is related to CD. Yeah? Then, what would we need for this to be true? This happens if and only if AD is equal to BC. That's the definition of this relation in the first place, yeah? Okay. So, would you get that BC is equal to AD? Yeah? That is the equal sign, the regular old equal sign we all know and love, is certainly an equivalence relation on the integers, yeah? Okay, so it doesn't matter which order you write things in. That is, we're going to inherit symmetry just from the symmetry of this other equivalence relation here that we're using to define our equivalence relation, yeah? Okay, so BC is equal to AD. Just unpacking it, this says that if I, oh, did I write this right? BC. Okay, so this will say, have I written this right? So, okay, and we'll have to write one more statement right here. This will give us that CD is related to AB. So if we want to look at what the statement is here, we take this one and that one and this one and that one, yeah? So we need CB equals DA. So BC is AD, and because of that, CB is DA. That just comes from the fact that you can do multiplication on integers in whatever order you want. Yeah? Bada boom. Okay. Maybe it feels like a kind of silly extra step, but just to be super clear, to show that this is, in fact, symmetric, we should appeal to these more basic properties. That is, that multiplication of integers is commutative, that the equal sign, regular old equal sign for integers, like, you know, and the way you've always used it is symmetric as well. Okay, bada boom. Finally, transitivity. So to show transitivity, assume that AB is similar to CD and CD is similar to what? EF, how about? Yeah, that's going to be fine. EF. Okay. that is AD equals BC and CF equals DE. What do we want to show?
AD equals
Let's think about it. What do we need?
AF.
We will show AF equals BE, i.e. that AB is related to EF. Okay, how can we do this? Feels kind of tricky. What would you do? You want AF equals BE. What would you do? Anyone got an idea? Solve for C and plug it in. Okay, so you're thinking of doing this. Let me kind of do a little tilde line right here. So we can go, okay, so if you're like C is equal to DE over F, right? And then you go, well, A D equals BC. And then you say, well, hey, that's B times DE over F. Yeah? And then you could like do something like multiply by F's. So ADF is equal to BDE over F times F. Yeah? And then you could go, hey, if I divide by D's now, I would get AF equals B, sorry, I'm making a mistake here, yeah? So I cancel my F's, so I get AF's. I have B, my F's will cancel out here, BDE, but cancel the D's, so BE. Yeah, which is what I want. Yeah? Okay, I think I'm seeing what you're saying. That's definitely a reasonable seeming approach. Now, one thing that you may protest at is you may say, but hey, it looks like we're using fractions here, yeah? After all, aren't we trying to do this to make the fractions, and now we're using the fractions in the process? What could you do? Is there any way to get around it? Can we look at this thing we want to do and somehow construct another way of getting there? Maybe we could use something like, okay, so BC, if I multiply an F, I could get that CF to turn into a DE, maybe? Let's kind of play around with something like that. Let's see if we can do anything there. That would be, I would say, like one of the next places you might try. If you start out with something you know, like AD equals BC, and then you go, okay, if I know that CF equals DE, I could go ADF equals BCF, and BCF would be BDE, yeah? Okay, that seems reasonable. And then you could use something like commutativity of multiplication, AFD equals BED, yeah? And maybe you could somehow, could we get rid of this D? What do you think? How can we get rid of this D?
Cross it off.
Yeah, I guess you could just cross it off or something like that. It's pretty reasonable if you wanted to think of it that way. There is perhaps a slightly easier way to go about this. So let me move this all the way through. Hopefully we've kind of thought about how you would just generically go about doing this sans the multiplication. Let me show you the ultimate manipulation that we end up doing. So let's start out with AD equals BC, and then go ADF equals BCF, and then ADF, yet again the same, equals BCF. And so this says ADF is equal to BDE. And this says that AFD is equal to BED, bed. AFD equals BED, just moving around the order of multiplication a little bit. And hey, this says that AF equals BE. But the step between here and here, we should perhaps be a little bit careful on. What is the justification for this? Well, effectively, what we want to say is fractions, but could you somehow prove this statement without appealing to fractions?
That like D over D is 1.
But now you're still thinking fractions if you want to say something over something as 1. That is, if is it true that xy equals zy? Is it true that that implies that x equals z? Well, not quite. What if y is equal to 0? Then it's not true. So this and y is not equal to 0 tells you that x is equal to z. Yeah?
Well, if 1 is equal to 0, it's supposed to be 0.
0 equals 0, yeah. But that does not mean that x would be equal to z necessarily, right? Yeah. So without this additional statement, the implication is false, since anything times 0 is 0. But okay, if you believe this, then this step is well justified. But if we wanted to be very careful, we should prove this step as well. Does that make some sense? Yeah? If you are fine with it, if you believe it, then I would say that that's like a perfectly reasonable explanation. You've got a number times d equals a number times d. D lives in the second coordinate, right? And remember, our field is, or not our field, our f here is z times the naturals, yeah? And so 0 not being a natural would tell us that indeed we have this condition right there satisfied, yeah? Okay, fine. All good. Now, I am belaboring this point that you should actually prove things like this instead of just relying on them. However, we will not prove this right now. Why? Because we would have to appeal to some of the basic properties of addition and multiplication involving integers. That is, we'd have to talk about some of the properties of the integers, like, for instance, the integers are a good example of a ring. But we haven't seen rings yet. That is, this isn't an abstract algebra class. I promise you that something like this is relatively easy to do if you start by building them out from like an abstract algebra perspective, and then you can go and appeal to like the basic definitions of multiplication and so on to make sure that this actually works. But since we're just taking our standard notions of multiplication and everything like that, not starting from first principles and defining everything out that way, we will skip that for the moment. But I want you to kind of have in your head the idea that all of this relies on addition and multiplication, specifically, I guess, multiplication here, of integers, right? And we have not actually sat down and defined what multiplication of integers is, yeah? So if we had, you can imagine, if we had set up regular old, multiplication of integers and like described its properties, that we could appeal to those properties from the definition of multiplication to show that this condition does indeed hold. Does that make sense? That is, in the background, we still have some of our like tacit kind of implicit knowledge, or some of our implicit knowledge about arithmetic floating around. Like we are not yet going through and formally, doing stuff involving arithmetic. We're just letting some of our intuition that we learned, in elementary school carry us on through. But if we wanted to be fully rigorous, we should start by doing things like that and then build things up more in a more complex fashion using that stuff. So I will leave that as an appropriate a step for now, saying it's okay, since we haven't gone through and formally like axiomatically define multiplication and everything. But you should have it in the back of your head that we are relying on some facts that we have not formally gone through and proven yet. There would be additional work. But all the same, we have up to that piece, and I guess we've got the same kind of thing going on here where we're saying like, hey, look, you can flip the order of multiplication, right? Yet again, more properties of multiplication of integers that we are relying on without having formally shown or defined in the first place. But up to that kind of hand waving, do you agree that this is an equivalence relation on F, the set of integers cross the naturals? All right. So with this, we can construct the rational numbers. Let's jump back to the other screen and do a little tiny bit of erasing. So the rational numbers will take to be these ordered pairs mod this equivalence relation. That is, we'll look at the equivalence classes of ordered pairs of F under this relation, and we'll treat these as our rational numbers. It will be easier for us intuitively, I think, to not write them as ordered pairs, though. So we will write them in the regular old fraction way, understanding these fractions as denoting ordered pairs, since after all, fractions do have an intrinsic ordering kind of thing to them. That is, 2 over 4 is not the same as 4 over 2, right? The spots matter. Okay, so if I can ever get this erased, I need to get a better cloth. There we go. So there we go. So now, with that in hand, let us define the rational numbers, Q, we'll call them, to be the equivalence classes of our F here, which is, if you recall, Z cross the naturals, integers cross naturals, under the equivalence relation we have here, i.e., we'll take Q to be the set of equivalence classes AB such that AB is in F. Notationally, from now on, let's write A over B to denote the ordered pair AB in F. That way we don't have to write any more ordered pairs. We can write regular old fractions. Way easier to see how to deal with them. Cool? All right. So one thing that's really nice is that all of our operations that we do on fractions can be done by picking any old representative element of an equivalence class. That is, if you want to multiply some fraction by 3/4, you get the exact same thing as if you multiply by 9/12. Wait, no, is that right? Yeah, 12ths, yeah, good. So let's show that. Let's go through and talk about it. Okay, so here, theorem. Suppose A over B, I will say, is similar now to x over y, and C over D is similar to W over Z for A over B, C over D, x over y, W over Z, all in our F here. Then AD plus BC over BD is equal to XZ plus YW over YZ. That's our claim. Okay, we'll prove this, but why on earth do we want to prove this? I wrote it out first so we can reach it kind of backwards to see that this is what we want. But effectively, the idea here is the following. So if I take A over B and I add it to C over D, what is the standard way of doing this? Well, we get common denominators. We go AD over BD plus CD over BD. Yeah? Or CB. Oops. CB over BD. That is, this is just AD plus CB over BD. Yeah? Do you agree with that? Okay, here's effectively what we're saying. If we add A over B and C over D, do we get back the same thing as if we add X over Y and W over Z when they belong to the same equivalence class? That is, if A over B, that equivalence class, is the same as the equivalence class of X over Y, and the equivalence class of C over D is the same as the equivalence class of W over Z, does this imply that A over B plus X over Y's equivalence class is the same as C over D plus W over Z? That is, if you want to add whole equivalence classes, if we want to extend our notion of addition to equivalence classes of fractions, does it matter which fraction we choose from the equivalence class to represent it? Does that make sense? No. Okay, yeah, so okay, you're answering it right on. No. Yeah, you're right, it doesn't. Yeah, good. Okay, I thought you were saying no, it makes no sense. I was like, no, okay. But basically what I'm saying is this. One natural thing you may want to do, anytime you've got a set with some sort of operation defined on it, and you can make some kind of equivalence class, is you can say something along the lines of like, hey, if I can take things like, A plus B, is it true that I can go, well, now I can take A, make a new operation on equivalence classes defined by just taking the equivalence class of the sum? Right? This is effectively what we're asking, is can we extend addition to equivalence classes just by pulling it inside? Does that make, yeah, I'm seeing some people giving me the look that says, I don't like that at all. Here's kind of the idea of it. If you have a way of putting things together in your original set, can you put things together in your set of equivalence classes by just selecting from each equivalence class a single element and putting them together in the original set and then taking its equivalence class? And what we're saying here is that for the rationals, yes, indeed you can. That is, what this is saying is that the fraction you get when you add A, B, and CD is the same as the fraction you get when you add X over Y and W over Z. That is, it doesn't matter which things you pick from each equivalence class to add together, the equivalence class they generate is the same. Yeah? Okay, so I'm looking at the clock and we are at time. So we'll show this next time. We'll go through it more formally, but this is like one of the kind of core ideas here, that you can take a big set, cut it down into pieces, and if you had a way of combining things in the big set, you now have a way of combining pieces by just combining representative elements of each equivalence class. Yeah? We'll see you next time.
Circle is just to show that it's two equivalents?
Yeah, I'm trying to say, like, look, this is like a new operation now. It's not the same plus, because now we're adding totally different things. We're adding whole equivalence classes. Yeah, we'll talk about it more next time. We'll make sure it all hits home. All right, cool. I'll see you guys later. Have a great day.